right, today we're going to deal with the fundamental theorem of calculus. So when you talk about the fundamental theorem of calculus, you might sit there, yeah, the fundamental theorem. This is what everything is based on in calculus, and yeah, part of it is in regards to what things are based on in calculus, especially when you get into Calc 2, Calc 3, and so on. But there's a lot of things that we've talked about that are dependent on limits, derivatives depend on limits. So there's a lot of fundamental ideas with respect to calculus. But this gets the title as a fundamental theorem of calculus. And we've dealt with some of the fundamental theorem of calculus already, but we will do a second aspect of it today. When dealing with the fundamental theorem of calculus, let f be the indefinite integral or the antiderivative of f. Okay, and this is the aspect of what we've already dealt with. So capital F is the indefinite integral or the antiderivative to little f of x. And then we're dealing with an integral, a definite integral from a to b. Our interval for our domain for x is from a to b of some function f of x. This can be calculated by evaluating our antiderivative of f at b and subtract off the antiderivative evaluation of our antiderivative at a. So we have f of b, capital F of b minus capital F at a. And this is what we have talked about already. This is what we've worked on already. So it's one of those things where this is nothing new. This is what we talked about last week in calculating a definite integral when working through the ideas of definite integrals. The second aspect of the fundamental theorem of calculus is an aspect that is not involved, the first part with respect to calculating a definite integral. But if you're given a function, a of x, of a of x is some antiderivative or definite integral from some constant. Now this must be a constant sum to x of f of t dt. This is an indefinite integral or an antiderivative of f that a prime of x is equal to f of x. And once again, this is one of those things where it starts out really muddy in your brain. But as we go through this, you'll see how we utilize our second aspect of the fundamental theorem of calculus. Basically, what the second aspect deals with, the second part of the fundamental theorem deals with, is everything in mathematics has inverse operations. Okay, addition of 5, subtraction by 5, multiplication by 2, division by 2, squaring something, square rooting something, natural log e to that value. So their processes are doable and undoable. Well, if you do the undoable process and connect them together, they should come back to where we originally started. Well, that's what this aspect deals with, is the derivative of an antiderivative of a function. So what occurs here is h of x is then going to equal the derivative of an antiderivative of a function. So we're taking the derivative of the antiderivative, or the integral of a function, from some constant c to g of x, of some function f of t dt. So we're trying to look at the aspect of function, doing an operation to a function, and then undoing the operation of the function. The thing I can relate this to is if we would take the sine of the inverse sine of 4 over 5. this would take us back to 4/5. We take a sine of the inverse sine, or if I would take the cos or inverse sine of the sine of pi over 6, okay, this will take us back to pi over 6. We're undoing and we're doing within the same line. But we're taking the antiderivative over the interval from some constant c to g of x, of some function f of t dt. This will equal the function evaluated, because when we take the antiderivative, okay, we have to evaluate at the lower function, we have to evaluate the upper function. Well, what we're dealing with here is we evaluate our function f at g of x, which is what we have here. But we have to also use our chain rule because we're looking at the idea of derivatives. So we have the idea of a chain rule there. So we have g prime of x. And if I wanted to, I could subtract off my function at c times the derivative of c. And when we take the derivative of c, that's a derivative of a constant. What we learned, this is the value of 0. So when you take the derivative of constant, you come back to the value 0, which will cancel out the second term. So what we're left with is the evaluation of our function at g of x times the derivative of g of x. For example, let's take a look at a problem here. We have d dx of some constant to 4x of a function 1 plus t squared to the 1/2 power. This should be dt, my bad. Now, what's going to happen here is, as I talked about, function and operation and inverse operation, they undo each other. But what we have to evaluate at 5 and we have to evaluate at 4x. So one of the things is you do and undo, just like we had if we have the cosine of the inverse cosine of 3/5. These do and undo. We come down to back to 3/5. That's once again what occurs here with the derivative and the antiderivative. So what we have to do to evaluate this is we substitute in our 4x. So we have 1 plus 4x squared to the 1/2 power. But then we have to use our chain rule because we're looking at the idea of a derivative here. So we take the derivative of 4x, so we multiply by a value of 4. And since we're dealing with a constant at the bottom, we can plug in the value of 5 and say 1 plus 5 squared to the 1/2 power. But then we have to take the derivative of 5, which is a derivative of a constant, which takes us back to 0. So what we are left with is 1 plus 16x squared to the 1/2 power times 4, or 4 times 1 plus 16x squared to the 1/2 power. And this is the second part of the fundamental theorem of calculus. So if we take a look at dx, once again, we have a value of pi there. When we have a value of pi, that's a constant. So when we have a constant, we still can deal with the same idea. So we have derivative, antiderivative here. They undo each other, so we're left with 2 plus, here's our function, x squared, all squared. We're just substituting in our function into here and for our t. But then we have to take the derivative of our function, which would be 2x. So we're left with 2x, 2 plus x squared, all quantity squared. We can also take a look at an area here. Okay, just redoing some of the ideas of areas. But what we talked about before when we were dealing with this, we have an area from -2 to 2 that we're trying to calculate this area between the graph of the function and the x-axis enclosed. So we have this area, and this area here. And as we talked about last week, we have some area, this area here is positive, this area here is positive, this area down here is negative. So we had to break our function, or our integral, into 3 functions at that point. So we have the integral from -2 to -1, because this is our value, -1, of our function x squared minus 1 dx. Please make sure you incorporate your dx there, because you're going to have to write out these functions. Then we have our second integral, the integral from -1 to 1 of x squared minus 1. This is going to be, and don't forget your differential dx, this is going to give you a negative area, so we'll take the absolute value of that. And then our third interval is from 1 to 2 of x squared minus 1 dx. So we have 3 different integrals that we have to take the antiderivative of. Well, the antiderivative in each one of these is going to be the same. We have 1/3 x cubed minus x from -2 to -1. 1/3 x cubed minus x from -1 to 1. And then 1/3 x cubed minus x from 1 to 2. So we have 3 of them that we have to evaluate. But once again, the second one here is going to give us a negative area. So we evaluate at -1, and then we evaluate at -2. So we have, let's see, -1/3. And you really have to watch your negatives as you go through this. -1/3 plus 1 is your evaluation at the top value, putting in -1 for x. So we have -1/3 minus the -1, which is plus 1. Then we subtract off, we need to evaluate at -2, so we have a -8/3 plus 2. And once again, really, this is the toughest part with these, is just dealing with your negatives sometimes. This will give us 2/3. And then we have minus 8/3, which is 2 1/3, plus 2. So we have minus a -2/3 here. So we have a total of 4/3 squares. That's my first area here from -2 to -1. Then we're going to have to evaluate from -1 to 1. So we're going to evaluate at 1. So we have 1/3 minus 1. Then we have to evaluate at -1. Once again, watch your negative signs. So we have a -1/3 plus 1 here. So we're left with a -2/3 here. Minus a 2/3 here. So we have a -4/3. We take the absolute value to give us 4/3 squares for the second one. And we can also look at the idea of symmetry. We'll probably get the exact same thing we did with the first one, but let's go ahead and go through the calculations. Evaluating at 2, we have 8/3 minus 2 minus, let's see here, we have 1/3 minus 1. So we have 2/3 minus a -2/3, which gives us a 4/3. So we have 4/3 squares with each one of these. So my total area is 4/3 plus 4/3 plus 4/3. So we have a total of 8/12, which is 4 squares. So that would be your total area. And once again, if we don't take the absolute value of the first one, or if I would just do the integral from -2 to 2 of x squared minus 1, what's going to happen is we would just get two of those things would cancel out, so we would just get a solution of 4/3, which is not going to be the total area because we have two of these values that would cancel out. The first one and the second areas would cancel out. The other type of problem you're going to run into is the idea of an absolute value and the antiderivative. To be able to evaluate this, we have an absolute value there. We have to go back to our basic definition. Absolute value of x is equal to x when x is greater than or equal to 0. Absolute value of x is equal to the negative of x when x is less than the value of 0. Well, what we have here is we have x minus 2. So wherever I see an x, I'm going to put in an x minus 2. So we can look at the absolute value of x minus 2 is equal to x minus 2 when x minus 2 is greater than or equal to 0. Well, if we look at that, this is when x is greater than or equal to 2. This will equal the negative of x minus 2 when x minus 2 is less than the value 0. That's when x is less than, adding 2, x is less than 2. So what this tells us is how we can clear our absolute value out of there. We can clear our absolute value out of there by utilizing this right here. X minus 2 is equal to x minus 2 when x is going to be greater than 2. It's equal to negative x minus 2, the opposite of x minus 2, when x is less than 2. So we can rewrite this antiderivative from the interval from 0 to 2. That is the interval that's less than the value of 2. This is equal to negative of x minus 2 dx. Then we can add to that the antiderivative from 2 to 5. This is the interval where x is going to be greater than the value of 2. So we're equal to x minus 2 dx for the second interval. So now we have two antiderivatives or definite integrals we have to evaluate. We have negative x plus 2, taking our negative through, and then we just have our x minus 2. So evaluating our antiderivative, we have 1/2 x squared plus 2x. We need to evaluate from 0 to 2. Added to that, 1/2 x squared. Oh, I lost my negative sign there. Negative 1/2 x squared. 1/2 x squared minus 2x that we have to evaluate from 2 to 5. So we have two antiderivatives we have to evaluate. We have to evaluate at the value of 2 first. So we have 2 squared, which is 4, times negative 2. We have negative 2 plus 4. Nice ones when we get the zeros in there. Minus 0. Plus, then we evaluated our second value. We evaluated 25. So we have 25 2's minus 10. Then evaluating at 2. So we have 1/2 times 2 squared, which is 4. So we have 2 here minus the value of 4. Once again, watch your negative signs as you go through this. So we have 2 here minus 0. 25 halves, that's 12.5. Minus 10, so we have 2.5. So we have plus 2 and 1/2 here. And then we have minus 2 minus 4, which is -2, minus a -2. These will boom ching to give me plus 2. So we're left with 2 plus 2.5 plus 2. So we have 6.5. Now, if we go to our calculator, looking at our calculator, we have the antiderivative. We would evaluate this antiderivative. Well, let's go to our y1. Let's get our absolute value of x minus 2 in there. We have the absolute value of x minus 2. So we can find our absolute value in our math button. We hit our math button. We go to number, which is option, the second middle one. First option is absolute value. Then we have x minus 2. Close our parenthesis out. I can see in my graph, my window is going to be bad here, so I'm going to have to adjust my window. If I go to zoom and go to standard 6, I can get everything in my interval or my graph. So we want to calculate second and calculate the antiderivative opposite 7 from 0 to 5. And once again, what will happen is it will color in, shade in, and you get 6.4999, which rounds to 6.5. Once again, you can utilize your calculator to give us a check. This gives us some additional problems to work with respect to absolute values and how to deal with absolute values. Also dealing with the idea of areas, once again, and also our fundamental theorem. What you have is a homework assignment. The first 4 deal with the fundamental theorem. Then we just go into more review of the antiderivatives. You can work on that. That will be due tomorrow. We'll go over some problems tomorrow. But once again, what we need to do is we need to keep things moving here. All right. QED, as done.